A relatively simple concept, Newton's first law explains one of the most basic principles of physics. The law states that an object in motion will remain in motion, and an object at rest will remain at rest unless acted upon by an unbalanced force. This is also known as the law of inertia. Inertia can be seen when driving a car. While performing a left or right turn at a relatively slow speed, the car will go in the direction you turn, but your body will want to keep moving straight. This demonstrates that your body will keep moving forward unless acted upon by an unbalanced force, in this case, being your resistance to keep your body aligned with the movement of the car. This law applies to countless objects and explains why theory does not always occur in reality. Take Newton's cradle. In theory, if the ball is dropped from a certain height, the ball at the other end of the cradle should rise to the same height, but in reality, this does not happen. The ball loses energy to sound and thermal energy, as well as friction. This is the same if you're riding a bike. In theory, the bike should keep moving forever, but external forces like friction, gravity, and air resistance forbid it. Friction and energy loss slows the bike as the road and the tires are not frictionless, and energy is lost through sound and thermal energy. Air resistance slows the bike as the rider and the bike are not aerodynamic, and gravity affects it as my road is not flat, goes slightly uphill, and slants to each side. When looking at Newton's first law, there are no real calculations, instead just simple diagrams. Take the example above. On the left, you have an object at rest with both the normal and gravitational force acting on it. On the right, you have an object accelerating downward due to gravity. These diagrams demonstrate the relationship between balanced and unbalanced forces and help us understand how objects move.
Newton's second law is vital to our understanding of physics, as it shows the relationship between unbalanced forces and momentum. In simple terms, this law states that unbalanced forces on an object will result in acceleration. The force will be equal to the change in momentum, represented with the formula F equals ma. F is net force, m is mass of the object, and a is acceleration of that object. We see this law constantly throughout our lives. This law even applies to the simple act of pushing an object, as you're creating an unbalanced force on that object, accelerating it in whichever direction you are pushing it. This law applies when you push open a door, when you pick up a pen, or even when you drop a ball. As I push this box, I exert an unbalanced force on it, causing it to accelerate and move forwards. We can use this formula to calculate how much force is applied on an object. If a 10 kilogram box is pushed forward at a speed of 4 meters per second squared, we can find that it will equal 40 newtons of force. We can also use that law to find the weight of an object, or the speed at which an object accelerates if we have the right info. For example, if we know that a 5 kilogram box is being pushed with 25 newtons of force, we can use the formula, rearranging it so that we can find acceleration. And as we put in the numbers, we can find that it will be accelerating at 5 meters per second squared. We can also use a similar process to find the weight of an object if we have the right data for that equation.
Newton's third law is an important concept when understanding the physics surrounding actions within nature. Newton's third law states that for every action force in nature, there's an equal and opposite indirection reaction. When understanding Newton's third law, the main question to ask is what happens when two objects interact with each other. A good example to further our understanding is this. An object is dropped and exerts a downward force on a table. Resultingly, the subject exerts an upward force on the object. There are two forces which result from this overall interaction: the force on the table and the force on the object. The magnitudes are the same, However, the directions of each force are opposite. We call the force exerted on the table the action force, and we call the force exerted on the object the reaction force. Therefore, we can break down Newton's third law by looking at the example. For every action force, there is an equal and opposite reaction. The ball in the example exerted the first action force, and the subject exerted the reaction force, which was equal in magnitude to the action force as well as opposite in direction to the action force. When regarding formulas, there really isn't a formula that pertains to Newton's third law, as it is more of an understanding. However, we can use the formula F subject equals F object, M subject is less than M object, and A subject is greater than D object. To make more sense of this formula, we can use the action-reaction force example of a bug hitting a truck's windshield. The action force pair which occurs is the truck hits the bug, and the reaction force is the bug hits the truck. Therefore, the object or the action force is the truck, and the subject or the reaction force is the bug. Bringing it back to the formula, we can finally see how we would specify the formula for this example. F bug equals F truck, M bug is less than M truck, and A bug is greater than D truck. Now let's take a look at a few real-life applications for Newton's third law. When you jump, your legs apply a force to the ground, and the ground applies an equal and opposite reaction force that propels you into the air. In aerospace, Newton's third law, when designing rockets and other projectile devices, is used. During the launch, the burning fuel exerts a downward force, and the reaction force pushes the rocket into the air. In space, the rocket applies its rear thrusters to move forward, which provides another example of how we can take advantage of the reaction forces in rocket designs. When firing a gun, Newton's third law is also applied by following the action-reaction pairs. The bullet pushes the gun, and the gun pushes the bullet. In conclusion, we can boil down our understanding of Newton's third law to the action-reaction force pairs. Where there is an action force, there will always be an equal and opposite in direction reaction force.